So a general rotation in 3 dimensions is parameterized in this form, is written in this form, j dot n psi. This is shorthand for this quantity here. Of course, n just contains 3 numbers, n1, n2, n3, such that the sum of the squares is 1, but j1, j2, j3 are 3 quantities which are themselves here represented by 3 by 3 matrices, orthogonal matrices, but they transform under rotations in a specific way.
Yeah. If we see j1, j2, j3, if we reduce in one column, so we are seeing that a Pauli Y matrix is sitting there.
Yes.
So what's the why Pauli Y is sitting
there?
there?
Good point. He says, look, there is a sort of Pauli matrix sigma 2 is sitting here in this case. So this means already it is giving you a hint that there is some connection between 2 by 2 matrices, namely the Pauli matrices, and the generators of rotations. Okay. So this connection is a very crucial one, it will become clear as we go along. But let me tell you right away that you can guess this by the fact that if you took the matrices half sigma j and set that equal to jj, half times the sigma matrix, these matrices also satisfy the same algebra. That is easy to verify, right. The commutator of any 2 sigma matrices is twice the third sigma matrix, and I take the 2 out by putting a half sigma matrix, and then it ends up with exactly the third generator. So what it is telling you is that, a very important point, that as long as I say that rotations in 3 dimensions are represented, are completely, the information is completely encoded in these algebraic relations, then the representation I choose for these matrices should be irrelevant completely. And it is suggesting to you that there is another way of writing rotations in 3 dimensional space, not just as 3 by 3 orthogonal matrices, but perhaps as some special kinds of 2 by 2 matrices as well.
So effectively, as we see in Pauli matrix, x sigma I sigma j is twice I epsilon I j k.
Yeah.
That directly follows from there. Means this commutation.
I mean, I write the 3 sigma matrices and I put this down and I explicitly show that this it satisfies this. So this quantity here is a Lie algebra of SO3, right. It turns out that Lie algebra has an infinite number of representations. You can represent these 3 generators by 2 by 2 matrices or 3 by 3 matrices or higher dimensional matrices, provided they satisfy this algebra. You need 3. And the lowest dimensional representation that is non-trivial is this 2 by 2 matrices. 1 by 1 they will just commute, as you can see, right. So 2 by 2 is the smallest one, and that is the property of the rotation group, that there exists a 2 by 2 matrix representation of these generators. So it suggests that there is a connection between orthogonal matrices and 3 by 3 orthogonal matrices and 2 by 2 matrices of a special kind. They will turn out to be unitary matrices, okay, and this we are going to talk about explicitly. So anyway, I wanted to point out that you have this possibility of writing it, and that is not just notation, as we will see later on. Okay. But now let us go ahead and see what this matrix looks like. What does I j dot n look like, or I times this? So let us put m equal to I j dot n. Let us call this matrix m equal to that, sorry, no vector there. Stands for this, and what does it give you? It gives you, we need to write this down explicitly, so there is an I, and then j1, so I need the 3 j's, I need j1 also. I have got j1 here, I have got j2 here, and let me write j3 here. This matrix is 0 minus I 0, I 0 0, 0 0 0. So what is j1 n1? Here is j1. So there is an n1 here and an n1 here at this point. So it is 0 0 0. Let me write it right there so that you can this thing. I need to multiply this by n1, so let us take out an I, or let us take out a minus I, and then this is a 1 and a minus 1, and I am going to multiply this by n1. So there is an n1 sitting here, there is an n1 minus n1 sitting here, okay. And then j2 n2, so I take out a minus I and this becomes a minus 1, so that becomes a minus n2. This becomes n2 here, and then the third one is minus I, and then this becomes n3 minus n3, okay. And then when I multiply by that I outside, these fellows will give me 1 completely, and I have this matrix down explicitly. All I got to do is to add these 3 matrices. So this quantity turns out to be 0, n3, 0, minus n2, and then minus n3, all diagonal elements are 0 of course, and then n1, and then there is an n2 here, and then a minus n1, and that is it. So that is what the matrix M is. And we can write down what M, the general element of M is fairly easily. So let us do that. I notice right away it is an antisymmetric matrix. The 1 2 element is n3, the 3 1 element is 2, and the 2 3 element is 1. So it immediately follows that M ij equal to epsilon ij k and k, that is it right away, contracted over k. So what is M squared ij? So M squared ij equal to M il M L j. So this is equal to epsilon il, I need some other symbol, let us call it k nk epsilon lj m n m. And I use the identity which tells me that this thing here once contracted is just a set of delta functions. So what will that give you? So let us put Lik with a minus sign, Lik. So this is equal to minus, and then you have delta ij, delta km minus delta im, delta kj, and then nk nm. And I use the Kronecker delta to simplify things. So this says m squared ij is equal to, well, out here I am just going to get a delta function, nothing more than that, nk nm. So this is contracted here, and that is 1, there is a minus sign, and this fellow gives me an ni nj. So it says ni nj minus delta ij, and that is it, okay. So what is m cubed equal to? And it is m squared times m, so m cubed ij equal to m squared ik m kj. And we know both these quantities here. Now this fellow, when it contracts with this guy, remember that there is an antisymmetry. This thing is totally antisymmetric, it will give you a 0, so you end up with the result which is equal to essentially minus this guy itself, so minus mij or m cubed equal to minus m. Okay. Right. So that is wonderful. We need to find e to the m psi and I am telling you that m cubed equal to minus m, which means that this exponential collapses completely, right, and e to the power m, therefore e to the m psi will be equal to the identity matrix some number plus something times m plus something times m squared, because m cubed will come back here and you can sum the whole thing up, right. So this means that we have actually achieved this task of exponentiating this special 3 by 3 matrix. As you know, you can write down the exponential of any 2 by 2 matrix fairly easily by just expressing it in terms of the sigma matrices, right. But 3 by 3, that is not true, there is no general formula, but in this case there is, essentially because these are, it is a sort of reducible representation and there are sigma matrices sitting here. Okay. So when you do that, you discover the so called finite rotation formula. So I leave this to you as an exercise to you to show that Rij in the general case, this is for n psi, is equal to the following. It is equal to cos psi times delta ij, that is the first term, plus 1 minus cos psi times ni nj, that is the second term, plus sin psi times epsilon ijk and k. Okay. So at the end of the day, you get an extremely simple expression which involves, as you would expect, the parameters psi and the components of n here, and this is what the ijth element of this 3 by 3 orthogonal matrix Rij looks like. Okay. Now you can ask, what does a vector do under this transformation? And it is clear that a vector does this: xi goes to xi prime equal to Rij xj. So you can write down what this guy is by simply putting xj out there, and what does it give you? So the first term, if you put an xj here, gives you just xi once again, so it is cos psi times xi plus 1 minus cos psi times xj with an nj, that is a dot product, right, and then there is an ni. So xj with nj is r dot n, that is a scalar, times ni plus sin psi times epsilon ijk xj nk. Okay. That is what the I component of the transformed vector, position vector r does. So we can write that down in vector form immediately, and since this is true for each of the indices, this immediately implies that under a rotation any position vector r goes to an r prime under this rotation n psi, and that is equal to, on this side, something which is it's a linear transformation. So the first term is cos psi times the original position vector itself plus 1 minus cos psi multiplied by r dot n times n vector, the unit vector here, for which the ith component has been written there, plus sin psi times, and do you recognize this? Epsilon ijk xj nk is the ith component of the cross product r cross n, right. So the third term is r cross n in vector form explicitly. So this says that if you took, in 3-dimensional space, if you took some arbitrary vector in this form r, and you took some axis of rotation n, and you rotated the coordinate system by an angle psi in the plane perpendicular to this unit vector n, then this r goes to r prime, which is a linear combination of the original r with a cosine here, and then a portion along the axis n, and a third part which is perpendicular to the plane formed by R and N. Okay. This is called the finite rotation formula. And you can easily check that if you had no rotation at all, you get r prime equal to r, because these two terms disappear altogether. And if r should be along n, then nothing changes, this thing vanishes identically, and if r is along n, you can easily see that points are not affected at all, no matter what size, right. So this thing here came about by actually physically exponentiating this e to the I j dot psi n times psi. We explicitly found out what the formula is, right. Now the point is, any vector, any set of 3 quantities is a vector, any C number ordinary vector is a vector if under rotations of the coordinate system the vector A goes to A prime, which is equal to cos psi times A plus A dot n n plus sin psi A cross n. So if this set of 3 quantities satisfies this finite rotation formula, then it is a vector by definition. The next thing you could ask is, and this is a subtle point, does J satisfy this rule at all? Not quite, because J is an operator, it is matrices, so we got to be a little more careful about how J transforms. It too transforms like a vector, but this is not the transformation rule for operators, this is only for ordinary vectors, right, whose components are all scalar numbers, ordinary numbers. Okay. So what we will do next time is to start with at this point and ask, is there another representation which we have got a hint about, namely the unitary representation for the rotation group in terms of 2 by 2 matrices, and then we will see which properties are independent of the representation altogether. We will also talk a little bit about, as I promised, the topological properties of this rotation group in the parameter space. Yeah.
So effectively then R in and R cross in, it forms a trihedral, right?
Yes, they form a triad, but not an orthogonal triad necessarily, because R and N need not be perpendicular to each other. Right. So in some sense, what else can the answer be? This is all it can be. It is a linear transformation. It should go to the identity when psi is 0, and then when psi goes to minus psi, you should have the inverse transform, etc., etc. All those properties are satisfied by this expression here. So one can give a kind of hand waving physical argument to say that it has got to be this, it has got to be a portion proportional to R, proportional to N, and proportional to R cross N, because these 3 will form a triad in 3-dimensional space in general. And then you can kind of figure out what the coefficients are, etc., by heuristic arguments, but this is completely rigorous. We have just explicitly found the exponential. This matrix n psi could be written down explicitly. We could write down the actual formula, closed formula for the finite vector, and it was just a cosine psi times delta ij plus 1 minus cosine psi times ni nj plus sin psi times epsilon ijk nk. So from this, the formula for the transformation of any vector followed immediately. Okay. Now the key point here is the fact that the 3 generators of rotations do not commute with each other. So the main point to notice is that this rotation is generated in general, R of n psi was the exponential of this quantity here, j dot n psi, where j was a set of 3 vectors and they satisfied the commutation relations jk jl equal to I epsilon k l m j m, where all the indices ran over the values 1, 2 and 3. Okay. Now we also noticed that these matrices J1, J2, J3, when we wrote them down as 3 by 3 matrices, they happen to involve something like the sigma matrices in between, one of the sigma matrices. And indeed it turns out that if I set J equal to 1/2 sigma j, then because of the properties of the Pauli matrices, these matrices here satisfy exactly the same algebra as was satisfied by the 3 by 3 representation of these generators. Okay. This is not an accident. Okay. The fact is that in 3 dimensions, rotation in 3-dimensional space is characterized by the Lie algebra of the infinitesimal generators J1, J2 and J3, and as long as you have 3 objects which satisfy that commutation relation, you have a representation of the rotation group, of the group of orthogonal matrices, etc., etc. So, you have actually a representation of this group, of the rotation group in 3 dimensions, which can have any dimensionality depending on what dimensionality these things have explicitly when you write them down as matrices. Okay. So, that is the important thing. This here, where this J is not necessarily a 3 by 3 matrix satisfying this algebra, but any set of 3 objects which satisfy this Lie algebra here is a representation of the rotation group. Okay. In fact, you already know that if you have, for instance, ket vector psi in quantum mechanics, and now you change your coordinate system describing, let us say this psi is the state vector of a particle, and you change your coordinate system by rotating it through an angle psi about some axis n. Then in general this psi would go to some other ket vector psi prime in the same space, which would be related to this psi, since nothing changes physically, the norm of psi does not change, etc., under this rotation. It would be related to this original psi by a unitary transformation. So, there would be some transformation u, some transformation operator u, which would be a function of this rotation that you did on the coordinates, and that would act on this psi. So, I write u of r loosely in order to tell you that it would depend on the parameters n and psi, of course, but the representation of this u does not have to be a 3 by 3 matrix, because after all it is acting on a ket vector, and that could be a ket vector in an infinite dimensional Hilbert space, in which case if for instance this psi is represented by an infinite dimensional column vector, then this u would have to be an infinite dimensional matrix again. But what is for sure is that this u is guaranteed to be e to the I j dot n psi. I am sorry to use this psi is a small angle here, the small psi, where this j comprises 3 objects j1, j2, j3 satisfying that Lie algebra, and the dimensionality of this j, if you write it as a matrix, would have to be compatible with whatever is out here. If this is an infinite dimensional column vector, then this j would have to be an infinite dimensional matrix as well, so that it could act, the exponential of it could act on that. Okay. So, here what has happened is that the rotation of the coordinate system has induced a transformation in Hilbert space given by the operator u, the unitary operator u. So, in that spirit, if I write Jij is half sigma j, then it is a matter of trivial verification that those 3 matrices satisfy exactly this algebra. Therefore, you expect that there exists a 2 by 2 matrix representation of the group SO3 in 3-dimensional space. Okay. Now, what is that representation explicitly? Well, here it is. All you have to do is to write u of n psi equal to e to the power I times sigma dot n psi over 2, and that is it, because these matrices sigma over 2, they actually satisfy the Lie algebra, and that is like of the general form, where these j's are represented by half the sigma matrices here. Okay. And why did I put a u here? Because you notice that because the sigmas are Hermitian, you notice that u is a unitary operator. It is easy to see that this will immediately imply that u dagger equal to u inverse. U is unitary. So, this here is a unitary representation of the rotation group in 3-dimensional space, but it is a 2 by 2 representation. Now, you could ask, oh, if it is 2 by 2, a 2 by 2 matrix, then how do I implement it in 3 dimensional space? I have points in 3 dimensional space specified by 3 coordinates, and it is convenient when I use the representation of 3 by 3 orthogonal matrices. What I do is to write the coordinates one below the other, x1, x2, x3, and then r acts on the left and gives me the new coordinates. Now what kind of thing object will u act on? It has to be a 2 by 2 object, either a column vector with 2 numbers, or it has to be a 2 by 2 matrix. These are the only possibilities. It can't be a column matrix with 2 numbers, because you actually need 3 pieces of information to specify a point in 3 dimensional space. So it has got to be a 2 by 2 matrix. And what is that matrix? Well, you already know that given any 3 dimensional vector, A made up of this ordered triple A3, you could construct the matrix A dot sigma, the 2 by 2 matrix A dot sigma, which is equal to, since sigma is 3 is diagonal, the usual representation, this is A3, this is minus A3, and then this is A1 minus IA2, A1 plus IA2. Specifying this matrix is equivalent to specifying A1, A2 and A3, and vice versa. So this could be taken as a representation of a vector in 3 dimensional space, 3 components, right, in which case a coordinate r would just look like, instead of r, the representation for this r would be x3 minus x3, x1 minus ix2, x1 plus ix2. So instead of r, I replace it by r dot sigma, which is this 2 by 2 matrix, and then ask what does a rotation do to it. Now since you got a matrix which is more like an operator than a column vector, it is clear that the way the rotation would operate is the following: just as r goes under rotation r in psi to r prime, the quantity r dot sigma goes under the same rotation now to r prime dot sigma, where r prime has components x1 prime, x2 prime, x3 prime. It is another 2 by 2 matrix that is related to the original 2 by 2 matrix by e to the power I sigma dot n psi over 2 r dot sigma e to the power minus I sigma dot n psi over 2. So it is u times this original matrix times u inverse on the right hand side, and it is easy to check that indeed you would get the finite rotation formula for the components of R. It is exactly the same thing, because if you wrote this out, this one here is this matrix here, and this is with the primes here, and then you compare, you discover it is just the finite rotation formula. For that you need to be able to write this explicitly down, the exponential of this 2 by 2 matrix. Now we already wrote the exponential of a 3 by 3 matrix, the R matrix, right. Yesterday the finite rotation formula did that. On the other hand, this thing here is easily written down by this little generalization of Euler's formula. It is cos psi over 2 times the unit matrix plus I sigma dot n sin psi over 2, and that is easy to verify. Okay. It has to be something like that, because any 2 by 2 matrix can be written as a linear combination of the unit matrix and the 3 Pauli matrices. So you could use that fact and compare coefficients, or you could explicitly find the exponential here using the fact that the square of every sigma matrix is the identity matrix. 2 distinct sigma matrices anti-commute with each other. So sigma 1, sigma 2 plus sigma 2, sigma 1 is 0, and so on, and then this formula pops out very easily after that. And all you have to do is to put that matrix here, r dot sigma is sitting here, and this is the same thing with psi goes to minus psi, or the complex conjugate, put that in here, and that is it. You verify that you get exactly the finite rotation formula. Okay. So what does this mean? This means that there is a connection between every 3 by 3 orthogonal matrix SO3, every 3 by 3 orthogonal matrix with unit determinant, every proper rotation, there is a connection between every such matrix and the corresponding matrix U in this case with the same parameters n and psi. So, there is a direct relation between these two. The question is what sort of mapping is this between one and the other. So, you have this set of matrices SO3, these are all elements of this points in this space, each point is a unimodular orthogonal matrix 3 by 3 matrix describing a rotation, and on this side you have a collection of matrices of the form of U. These are unitary matrices and they are 2 dimensional, so one writes it as U2 and the determinant is also 1 as you can easily check, and it is SU2. This is the special unitary group of 2 by 2 matrices with possibly complex entries in general, and there is a connection between this and that. Okay. The question is it a 1-to-1 connection for every matrix here, do you have one matrix here or vice versa? The answer is you don't, it is not a 1-to-1 connection because of this fact that if I change U, this is U r dot sigma U dagger, but if I change U to minus U, U dagger also becomes minus itself, but r prime dot sigma does not change. Okay. So, it is immediately clear that if you give me a particular R here and there is a matrix U here, minus that matrix gives me exactly the same physical rotation before. Therefore, there is a 2-to-1 connection between them. This is called a 2-to-1 homomorphism from SU2 to SO3. Okay. Both these fellows map onto the same point. SO3 of course, we need a little more to assert this. SO3 of course is parameterized by 3 real parameters. The components of the unit vector n, 2 of which are independent because the sum of the squares is equal to 1, and the angle psi. So, there are 3 real parameters in this space. Every element here is parameterized by 3 real parameters. That should be the same here, otherwise there is no question of mapping from one to the other. So, we need to know what is the most general form of a 2 by 2 matrix that is unitary and has determinant equal to 1. Now, if I write a general 2 by 2 matrix in general with complex entries, it has 8 independent parameters because there are 4 elements and each of them is complex in general. So, there are 8 independent parameters. Let us count the number of parameters in SU2. So, let us write a general 2 by 2 matrix M, and let us write this in the form alpha, beta, gamma and delta, some complex numbers alpha, beta, gamma, delta, and then impose the condition that this be unitary and let us see what happens. So, M dagger in general is alpha star, delta star, gamma star, beta star, complex conjugate transposed in this form. And then let us construct MM dagger, this is equal to mod alpha squared plus mod beta squared, that is this term, and then alpha gamma star plus beta delta star, and then out here you have alpha star gamma plus beta star delta, and then mod gamma squared plus mod delta squared. And you want this to be unitary, so you want this to be the identity matrix in this case, and then we solve for these elements and see what happens. So, we right away have mod alpha squared plus mod beta squared equal to 1, which is also equal to mod gamma squared plus mod delta squared. So, you got 2 conditions, so 2 of the parameters are gone, eliminated, and then the off diagonal element alpha star gamma plus beta star delta equal to 0. Let us eliminate delta, for example, delta equal to minus alpha star gamma over beta star in this fashion. Okay. The other one is just a complex conjugate of this condition, it does not give you anything new. Okay. But we also want to find out what the determinant condition says. So, you want to put in the determinant and see what that does, and what is determinant of M equal to? It is a unitary matrix, right. That is the matrix analog of a complex number with unit modulus. And what is the most general form of a complex number with unit modulus? E to the I some real number, right. So, it says determinant of M must be of the form e to the I theta, where theta is any arbitrary real number because it is a unitary matrix. Okay. This of course immediately says this is equal to alpha delta minus beta gamma equal to e to the I theta, okay. And you can once again eliminate one of the variables favors. So, what shall we do? So, let us see. We will do this in a little more efficient way. I would like to do this in a little more efficient way. So, if I put this in, so this is equal to alpha delta, so that is minus mod alpha squared gamma over beta star, that is this term here, I put in this value of delta here, minus beta gamma, that fellow, which is equal to minus mod alpha squared plus mod beta squared gamma over beta star, which is equal to minus gamma over beta star, because mod alpha squared plus mod beta squared is 1. Okay. All I have done is to simplify this and use that condition here. So, if I put that in, minus gamma over beta star, this says delta is equal to, and that should be equal to e to the I theta. So, it says alpha star e to the I theta, delta is equal to that. Okay. And similarly, gamma is equal to minus beta star e to the I theta. Okay. That is just this condition here. So, it says the most general 2 by 2 matrix, which is unitary, must have the following form. So, the general 2 by 2 unitary matrix must be of the form, let us write that down, there is some complex number alpha, then there is a complex number beta, and then a minus beta star e to the I theta, and then delta, what was that, alpha star e to the I theta, with a condition mod alpha squared plus mod beta squared equal to 1. That is the most general form of a 2 by 2 unitary matrix. And determinant equal to e to the I theta. Okay. How many parameters are there in this? How many parameters are there in this thing? Why do you say that?
Because is complex.
There, how many real parameters are there? When you count parameters, you have to count how many numbers do you have to specify independently. Right. When you specify a complex number, you have to specify both its real and imaginary parts, which you can do independently. So, that should really be counted as 2. So, what is the total number of parameters in this?
3 and 1 is reduced.
Yeah, there is 3 because between alpha and beta you have 4 parameters, but there is one real condition between them. So, there are 3 independent numbers here and there is a theta. So, this is a 4 parameter group. That cannot match the rotation group in 3 dimensions because that is a 3 parameter group. But the moment you make the determinant equal to 1, then theta must be 0, right, because you are saying the determinant is e to the I theta must be equal to 1. So, this means that SU2, so this is U2, this is the group U2 has 4 parameters, SU2 has 3 parameters. The homeomorphism that we are talking about, the homomorphism is between SU2 and SO3, okay, and e to the power I sigma dot n over psi over 2 is a unitary matrix with determinant 1, as you can easily check. And what is the most general form of this matrix in SU2? What is the most general form of an SU2 matrix? Put theta equal to 0 and that is it. So, the general SU2 matrix is alpha beta minus beta star alpha star satisfying that condition with mod alpha squared plus mod beta squared equal to 1, or if I write it in terms of real parts and imaginary parts, and the claim now is that you have 2 matrices in this space, in this group of matrices SU2 corresponding to each physical rotation in 3 dimensional space.